All right, let's look at our 2019 problem number 3. This one was heavy with probabilities, and you also are going to want to be using the formula chart. It has conditional and independent probabilities. So let's take a look at this real quick before we get started. So here on your formula chart, you have this uh, right here. This is the union. So or A or B would be the A's plus the B's minus the intersection of A's and B's. So remember that. And then here, this is conditional. The probability of A, given that, that's conditional, B has happened. So that's out of the total B probability, out of all the chances of B happening, the part that is A and B, the intersection out of the total. Now, something that is not on the formula chart, which is used in this problem, is the idea of proving or computing to check and see if two variables are independent. So in this case, we used this overall rate of A, and then the rate of A, this is conditional upon B happening. Because essentially what this is saying is, given that B has happened, the probability of A remains the same. Therefore, B did not change that probability. So if these two values are the same, B did not change that probability, and therefore A and B are independent. All right, so all three of those things come into play with this problem, 2019 number 3. So here we go. We had a table of values. The part A was just reading from the table and using those formulas. So A was about never and, of course, this was about never, sometimes, or always taking your medicine as prescribed. Okay, so the never and a woman. So that's just the intersection. So that's this area right here where we had this intersection of never and woman, 0.0636. So part 2, what's the probability that it's never or who is a woman? So that's collective, all the never plus all the women, but don't double count this intersection. So that is this here. See, the overall women probability plus the overall never probability minus the women and never that you just computed in the first part. So there's how we get that right here is shown 0.12 plus 0.53 minus the intersection. And there's your 0.5864. So part 3 is a conditional probability. What's the probability that the person selected whose response is never, given that the person is a woman? So that's our conditional right here. So we are going to want to put the total women probability on the bottom, which is 0.53. And then on the top, we want the intersection of never and woman. So that's from part 1, 0636. So that looks like this. See, overall woman, never and woman. And so there's 0.12. Now, they very carefully set you up with all of these things because you're going to use them in Part B. Part B says, for the people surveyed, are the events being a person whose response is never and being a woman independent events justify? Now, real quickly, you would get full credit for Part A. So you would get an E if you had all three of these numbers with the accompanying work. And you get a P if you just had 2 out of the 3. All right. So in Part B, we had to say, to get credit, you had to say, yes, they are independent. So don't forget to answer the question. And somehow explain it. If you only explained it with this sentencing here, if the events never and women are independent, then the fact that you're a woman would not change the probability that you never take your medicine as prescribed. If all I did was that without support numerically, then I would get partial credit. But I could just say yes and then support down here the appropriate way with numerical support. See, overall, the probability of never was 0.12. So if you think about it here on this formula chart, that's putting never for A, overall never, and then the conditional never, given that you're a woman. Okay, so that's what I did here. Overall never, and then probability of never, given that you're a woman, was from this part 3 right here. So therefore, since those two probabilities are the same, the events never and women are independent of each other. And so to get credit on that one, you had to show a couple of, you could justify your answer a couple of ways. You could say, show how the probability of woman and never, so the intersection is the same as the overall woman times the overall never. So that's nice, because if you can multiply probability of A times probability of B and it equals the probability of A and B, that's another way that you can indicate that. In fact, I'm going to type that in there because I do like that on this formula chart, that you could kind of support it that way. Here's one way. Probability of A times, um, what would that mean? Times the probability of B equals the probability of A and B. Okay, so if you can show that, you can, which is what they did. All right, but technically the more appropriate way is one of these two, never given woman or woman given never, which you had just done that in the previous section, so probably that's the way most people went. All right, and you get partial if you said they're independent, but you give explanation of what that means, but you didn't support it with numerical response. All right, so there's your E, P, or I for part B. Now let's go to part C. Part C says, assume that in a large population, the probability the person will always take the medicine as prescribed is 0.54. So that's just reiterating what we have here. They say, if 5 people are selected at random from the population, what's the probability that at least 4 of the 5 people will always take their medicine? So I hope that you recognize this is discrete, where in order to have at least 4 people taking it, then we have exactly 4 people taking it, or exactly 5 people taking it. The catch is there can be many different combinations of where those 4 people are sprinkled, and then where that fifth person, or well, and then you have the everything. So the idea is you had to indicate this is a binomial distribution, not doing a normal model with samples of size 5. Because you can't, if you did a normal distribution with samples of size 5 and a sampling distribution of the samples of size 5, the large enough condition would not have been met. So that would not have been able to be done. You lost full credit there. So with this situation, what you should recognize is this right here. So we are wanting probability that X is greater than or equal to 4. And then N is your number of trials. So that was out of 5 people. I want 4 successes. And then you do the probability of success and failure. And then do the same thing again with 5. So it looks like this. Here's the 5 choose 4 successes, 4 successes, 1 failure, plus 5 choose 5 successes, which is 0.54 to the fifth and 0.46s. Then that computes to this number here. If you wrote this formula out, but then you did not get the correct number value, you got partial, okay? Because you had to indicate that this thing was a binomial distribution. And by doing this work here, you satisfied 2 criteria indicating it was a binomial distribution with a n of 5 and a p of 0.54. So this gets you a lot of credit when done. properly. So the way I did this in the calculator, you could just do the PDF of 4 plus the PDF of 5 and add together two PDFs. Or you can do 1 minus the bottom section and take off the 3 and below, which would leave you with 4 and 5. So those are the two options calculator wise that you could do that. And again, to get that credit, you had to indicate this binomial distribution, the correct boundary values of 4 and 5 you wanted, and then the correct probability to get essentially correct. Partially, you have to do part 1 is definitely required. It's a binomial distribution with n of 5 and p of 0.54. If you didn't do that, you were out. But if you did that and then you only got one of these other parts, 2 or 3, then you get a partial. All right, so then this is the same idea. See here in the notes, this right here gets you components 1 and 2 satisfied. Then you just had to give the correct answer. And look at here, if the response is this, you get nothing. Okay, so that's worth noting. All right, the calculator speak gets you nothing. And so then here we go. You got your EEE, EEP, and so on. It's the same 3-part conclusions as these. All right, so we'll see how you did. And that's the conclusion to your 2019 problem number 3.